What's up, chemistry? Welcome back to the dirt bike shed. We're about to wrap this thing up here. Today we're going to have a lesson on acids and bases. Acids and bases. So here we go. Check it out. I've got some water here. Just water. I just poured a little bit of distilled water into a cup. Now, I could drink this water and it would taste like water. And most of you kids would say that water tastes like nothing. Well, that's not true. Water tastes like water. Now, if I was going to ask you to describe this pure water with nothing in it, and I said you have three choices. Is this either acidic? Is this basic? Or is it neutral? You'd all say neutral. Now, what does neutral mean? What is an acid? What is a base? Let's find out. If I write the formula for water, you used to seeing it written H2O. Another way to write the formula for water is HOH, and I mentioned that earlier in the year. HOH. See how there's still two H's and one O? Now, if I took this water molecule and I tore it in half, you'll have an acid and a base. Look, tearing it in half, you can't tear this oxygen in half. So one half of the water is this H here. The H has a positive charge. The H is the acid. It's called hydronium. The OH has a negative charge, and you've seen that a bunch of times. What's the name of OH negative? You're right, the name is hydroxide. So this is hydronium, this positive hydrogen, and this is hydroxide, this negative hydroxide. And if you put these two back together, beep, boop, you'll have neutral HOH again, or what we call H2O. So the crazy thing when we talk about acids and bases is the H from the water is an acid, and the OH from water is base. Isn't that cool? Now let's take some neutral water and turn it into an acid or an acidic solution. I can get something as simple as HCl. Now the name of HCl is hydrogen chloride, or you may know it as hydrochloric acid. If I take an H atom and a Cl atom stuck together, HCl, and I have a powder of it, right? I've got quadrillions upon quadrillions of these HCl's. I can put this powder in water and make an acid. Let's take this apart right here. This is pretty crazy scientific. I'm so scientific here. I'm going to take this compound of HCl. I'm going to take this compound of HCl and I'm going to throw it in the water and it's going to dissolve. Now what's going to happen when it dissolves? Well, the bond between the H and the Cl is going to break, right? So if I take this HCl and I throw it in the water, it's going to dissolve. Let's do it. So here's my water. I've got a mixer going. This is neutral water right now. I'll turn the mixer down a little bit. I'm going to take some hydrogen chloride, right? And I'm going to throw it into the water. Beep. Now, the H and the Cl are going to break apart. See how the H and the Cl have broken apart? Okay. And what does that mean? It means that now the positive H and the negative Cl are swimming around separately in the water. They're separate ions, okay? Now, the Cl we're not that worried about unless we're making sure our pool is safe. The H is what's going to cause us trouble. So we're watching this happen. We have HCl, we have hydrogen chloride, which is what it would be called if it was still a solid, right? And we're going to drop it into water. And you've seen me draw pictures like this before. Here's a beaker of water, okay? And when the H and the Cl hit the water, they separate into a positive H and a negative Cl. That's what dissolving is, right? That's what dissolving is. Well, we drop a bunch of HCl's in here, and they separate into positive H's and negative Cl's. And now we have an acid. This water is now acidic because of these free H's floating around. Remember earlier I said, just a second ago, I said that You have HOH, that's the formula for water. This is the acid, right? And this part is the base. So when you pour something like HCl into water and it dissolves, you end up with these free protons. What do you mean proton? Well, here's a hydrogen atom. It's a proton with one electron circling it, right? So for this hydrogen atom to become positive, that means it doesn't have the electron anymore. So an H plus is literally just a proton. Isn't that crazy? Free proton. So when you have water with H pluses floating around in it, that's what we call acid or acidic. Crazy. Now check out the opposite. What if I have a powder like NaOH? What's the name of NaOH? Sodium hydroxide, right? I'm going to drop some sodium hydroxide into a beaker of water. Well, what do you think is going to happen? Okay, yeah, you're going to have a positive Na and a negative OH. And the more of these little bits of powder that we drop down in there, the more OHs and the more NAs you'll have that are free. Now, we wouldn't be dropping 3 of these. We'd be dropping 3 trillion of these, because we're talking about tiny, tiny things. So the NaOH dissolves, and you've got Na positive and OH negative. Guess what? What would this solution be? This solution wouldn't be an acid, would it? That's right. This solution will be what we call basic, right? Why would it be called basic? Because it's got OHs that are free and floating around in it. Remember, once again, this is a water molecule, HOH. The H is the acid part, the OH is the base part. When you have OHs free floating around in water, when you have hydroxides floating around freely in water, then that water is a base now. Okay? That's what an acid and a base are. So now I'm going to write down a bunch of compounds that could be dropped in water and dissolve, and you try to think to yourself, would this make an acid or a base? All right, I've got HCl. Would that make an acid or a base? An acid. How about NaOH? Would that make an acid or a base? That would make a base. How about HF? Would that make an acid or a base when it dissolves? It would be an acid. That's right, because the H is going to be free. What about calcium hydroxide? What's that going to make? Acid or base? That's going to make a base. So the simplest way, and this isn't the only way, okay, but the simplest, most basic way is, if you're looking at formulas that start with an H, right? Like HI would be hydroiodic acid, HNO3 would be nitric acid, HClO3 would be chloric acid, HCl would be hydrochloric acid. Look at these guys. These guys that start with H, they're going to be acids. And these other guys that end with OH, like NaOH, CaOH2, what about magnesium hydroxide? These guys that end with OH, potassium hydroxide, these are going to make bases, right? These are bases. When they get in the water, they're going to make it basic. Isn't that super easy? Now, this is the simplest way to define acid and bases. And this is the Arrhenius definition. Arrhenius, I've forgotten how to spell that. Arrhenius, hang on, I'm going to Google it. I was on my way to being wrong. Arrhenius. This is the Arrhenius definition. Free H's are acids, OHs are bases. There's a little more complicated way to do it, but we don't have time. Now, acids and bases have some very simple characteristics. Okay, acids are like fruits, and they're sour, and they eat metal, and bases are basically soaps and things we clean organic things with. They feel slippery, they taste bitter. But we're going to do that in another video, okay? Right now, we're just going to stick with some chemistry, all right? Now, we always tie the entire course together. So remember, we were just talking about molarity, and molarity is the strength or concentration of a substance, right? If you dump in a lot more powder, then you will have a higher molarity solution, right? So let's say you dumped 58 grams of NaCl, and that's the molar mass of NaCl, and you dumped it into 1 liter of water, then that would be 1 mole per 1 liter, and that would be a 1 molar solution. There, that's my quick review. Now, you're about to learn something. Some of you smart and curious kids are going to be like, wow, I've always heard of this, now it makes sense. Let's talk about dumping some hydrogen chloride into water, okay? There's a little bit. There's more. Dumping a bunch of it in there. And there's basically 10 times as much. This water would be more acidic. It would be more acidic because it's got more H's, right? Like, you would not want to put your finger in there, right? You'd be like, owie. Because this is a strong acid. You wouldn't want to get this in your eye, right? Because there's so many free H's. Now, how do we measure the amount of H's dissolved in there, right? Molarity, right? The more of this we dump in, the higher the molarity. And that is where the pH scale comes from. What? That's right, the pH scale. The percent hydronium scale says that the more of this we have dumped in, we're going to change a number. All right? We're going to change a number. And that number we're going to change is the pH. Okay? Now, I've taken the hydrogen chloride away. And I'm just going to draw you a neutral vat of water. Now, the neutral vat of water, we've got a liter of water at room temperature, okay? It's going to be filled with trillions and gabillions and quadrillions of HOHs. I mean, literally, that's what it is, right? This is water, correct? Now, you'll remember that water is a very polar molecule, and it's held together by hydrogen bonds. That the molecules are held to each other, right? By like there to there, there to there, there to there, by hydrogen bonds. So water is very strong. Water can dissolve things easily, but you know what water also dissolves? Boom, boom, boom. Water dissolves itself. What? Yeah. It dissolves itself. Water tears other water molecules apart. And guess what happens when you tear? Let's tear this guy right here apart. Rip. All right, I just ripped it apart. I ripped the H off the OH. Guess what I've got now? A free hydrogen, an H plus, and an OH. All right? So water is literally acidic and basic equally. That's why we call it neutral. So you have free H's and free OH's, and then these two guys will collide, boop, boop, and a moment later, they'll be right back into HOH, okay? Now, why are you telling me this, Mr. Perkins? Because that's where the pH scale comes from, okay? The pH of neutral water is 7. The pH of neutral water is 7. What does that mean? It means this. Now, I'm not showing you all the HOHs that are still stuck together. I'm not showing you the trillions and trillions of those. I'm just going to show you the free H's and free OHs that have been ripped apart, okay? So we take this guy, we rip it apart, and put an H and an OH. Now, when we talked about molarity, in a liter of water at room temperature, okay, in a liter of water at room temperature, do you know how many moles of free H's would be in that water? What the molarity of neutral water is? If the water is neutral, right, then that means we have 0.0000001 molar H plus in there. What? Yeah, Mr. Perkins, that is a very low molarity. It is. And since we have equal H pluses to OH negatives, then wouldn't there also be 0.0000001 moles of OH in there? Yes, there would. Now let's look at this number. If I was going to write down the molarity of how many free H's there are floating around in a liter of water at room temperature, okay, I would say that the molarity of that water is 1 times 10 to the negative 7th molar H plus. Wait a minute, Mr. Perkins. That number 7 looks familiar, yes. This number right up here, which stands for how many places over this 1 is, isn't this 1 in the negative 7th position? This number and this number are the same number, right? That number right there, the negative log of the molarity, is the pH. So really, the higher the pH, the lower the number is. Let's look at a pH of 8. That would be 0.000000. And now we put another 0. That will be something that had a pH of 8. Does that make sense? A pH of 8 means there's less moles of H plus in the water than a pH of 7. How many times less? 10 times less. So neutral water has a pH of 7, and guess what it also has? A pOH of 7. Isn't that crazy, right? Because wouldn't there be an equal H plus and OH negatives? Does this make sense to you? Okay, we're going to do a little math with this. Now, if I have 0.0000001 moles of free hydrogens, then that means I'm going to have 0.0000001 moles of hydroxides. Because remember, we're tearing apart HOH, so for every H, there's got to be an OH. That's how we're neutral, okay? Things that are neutral have a pH of 7, and they are safe for you to drink, and that's neutral water, okay? Now, notice that we have a pH of 7. Well, there's also a P for OH. You've probably never heard of that, but the percent OH is also going to be 7. What do those two numbers add up to? 14, that's right. Where do you know this number 14? Where have you seen it in middle school science? That's right. The pH scale goes from 0 to 14. This is where that comes from. Okay, and if you're in the middle and you're neutral and you have a pH of 7, then that means you have to have a pOH of 7. The pH and the pOH will add up to each other, okay? Now, when we end up having more H's, that means that there are less zeros right here. Wouldn't that be a higher concentration? So then the pH goes down. So if something had a pH of 6, it would be acidic, like milk, okay? It would be slightly acidic. But for you to have a pH of 6, you have to have a pOH of what? If the scale only goes up to 14, you'd have to have a pOH of 8, because 6 plus 8 equals 14. The pH and the pOH always add up to 14. Now look what that means. That means if you have this much pH up to 6, then the 6 of 14, the rest of it is going to be the pOH. So the pH, if the pH is 6, the pOH is 8. They complement each other. They add up to 14. Having a pH of 6 means that you have more hydronium, more H's, than you do OH's. Remember, these are the very small numbers over here, okay? So we can write this simple statement down, and you're not going to like the way it sounds. If we have a pH, if we have a pH of 7, that means the molarity, there's 0.0000001 moles of free H's in there. Now, a better way to write that is in scientific notation, 1 times 10 to the negative 7th, okay? So the pH is 7. It's that number right there. Okay, now I'm going to write this as a sentence. The pH is the negative log of the molarity. So in other words, if you typed in this number in your calculator and you took the negative log of it, you'll get the number 7. It's that easy. Let's do some of those. All right, I've got a calculator, and I've got 3 problems for us to try. I'm going to show you how to do the first one, okay, before I ask you any questions about it. The pH blank. What is the pH of 0.01 molar HCl? There's 2 ways to do that. One, you can say, well, the number 1 is over 2 places, so the pH is going to be 2. That would be correct. Another way to do it is you type in 0.01 on your calculator, then you hit log, and then you hit negative. You get the number 2. Now, your calculator may have a different order. On the bigger calculators, I think you have to type in negative, log, and then in the brackets you put 0.01, close the bracket, and hit equals, okay? And then it'll give you the number 2. So why don't you tell me, what is the pH of 0.0001 molar hydrofluoric acid? Okay, what is the pH of that? Okay, I can see the answer is going to be 4 because the 1 is over 4 places. But I'll take my calculator, 0.0001 log negative. Boom, gives me the number 4. Let me ask you about this one. What is the pOH? Okay, so now when we solve this, we'll just be solving for the percentage of hydroxide. You can do that. 0.00000001. I believe that 1 is over 9 places. So I believe the pOH is going to be 9, but I'm going to try it on my calculator to be sure. 0.00000001 log negative. Yep, the pOH of that is 9. All right. If the pOH is 9, then what is the pH? I already taught you that. What is the magic number that the pH scale goes up to? It goes up to 14. So the pH is 5. If you have a solution and the percent of hydroxide is 9 and the percent of hydronium is 5, they have to add up to 14. Now, I'm going to give you 2 more where you can't count the decimals, and you're going to need to solve them using the same order on your calculator. What is the pH of a solution that is 0.000741 molar HCl? All right, see, now you can't count how far over you're going because you don't have a 1 there. You've got numbers. So you have to take your calculator and hit 0.000741 log negative. And you get the pH is 3.13. All right, what is the pH of a solution that is 0.000143 NaOH? Super trick question. NaOH. What is the pH of a solution that has a molarity of hydroxide of 0.00143? Remember, we got to worry about this number 14 is all. All right? So that to complement, the pH will complement the pH.